The discovery of the Higgs boson is a fantastic success, but there's so many things that we don't understand about it. We don't understand, what's going to happen to the future in the future of the universe, because with our current measurements of the Higgs boson, it looks like empty space is unstable and it's going to collapse. Well, we don't believe that, so we believe there must be new physics to prevent that from happening. Also, we don't understand why particles have the masses that they do. So we know that the Higgs gives masses to particles, but we don't have a theory of how big those masses are. We just know it's possible, but we don't have a theory of how big they are. So there's many issues that are raised by the discovery of the Higgs boson for us theorists to think about. So the universe, obviously it contains matter that we see about us, but the astronomers tell us that there is much more invisible dark matter which we can't see. We can see that it has effects through gravity, but we have never detected directly this dark matter. So that, I think, is one of perhaps the most important issues in physics and astronomy and cosmology today. What is the nature of that dark matter? We think it may be made of particles, maybe particles that we can make at the Large Hadron Collider at CERN, and that's certainly one of the things that we're working on very hard at the moment. But there's many other issues that we don't understand. How did matter originate in the first place? Why is there any matter at all and not just radiation? We would like eventually to understand why the universe is so big and so old. We think that we could do that in terms of the properties of particles, but it would have to be particles beyond the standard model. And well, eventually we would like to come up with a quantum theory of gravity and unify all the particle interactions, and that is definitely something beyond the standard model. So we believe that the universe started off in a very hot and dense state, and probably with equal amounts of matter and antimatter. Then as the universe expanded, somehow some asymmetry grew up between the amounts of matter and antimatter. And now, of course, in the universe today, we see matter, but we don't see any large amounts of antimatter in the universe. So the question is, how did this difference between the amounts of matter and antimatter arise? So we think it goes back to the properties of the particles themselves. And in fact, in the laboratory, we do see small differences between the behavior of matter particles and antimatter particles. So we think that's connected to the cosmological difference between the densities of matter and antimatter. But we're still trying to work out the details of that.
antimatter particles have the same masses as regular particles. They have opposite electric charges. So for example, the electron has a partner called a positron, which has the same mass but opposite electric charge. Now, people thought for a long time that the behavior of matter and antimatter was exactly equal and opposite. But then it was discovered in the 1960s that that's not quite the case. If you're looking at the weak interactions responsible for some forms of radioactivity, these behave slightly differently for matter particles and antimatter particles. And this was discovered first of all, as I said, in the 1960s in the decays of particles called kaons. And kaons and antikaons behave slightly differently. And now we've seen this in the decays of other heavier particles, and we're trying to understand what causes this difference and whether there's some possible connection with cosmology. According to many theories, not all, but many theories, dark matter could be made of particles which don't have any electric charge, so they don't shine. They interact very weakly. And these particles, in many theories, weigh between 100 and 1,000 times the mass of the proton, and they could, in principle, be manufactured at the LHC. So one thing that we're doing is we are colliding protons at the LHC and hoping to make dark matter particles. Another thing that you can do is you can look for particles of dark matter hitting particles of regular matter. We know that there's dark matter all around us. If it's made of these particles, then those dark matter particles are passing through us all the time, but they interact very weakly, so no problem. But if you go into a deep underground laboratory, so shield yourself from cosmic rays, and you have very low radioactive background, you can hope maybe to see interactions of dark matter particles with regular particles. So there's experiments around the world looking for the scattering of dark matter particles and regular particles, and of course at the LHC we're looking for the production of dark matter particles. So far we haven't found anything, and in fact just a week ago there was a new result from an experiment in China which gave the best limits of the scattering of dark matter particles on regular particles, but we're still looking. So the top quark is the heaviest particle that we know. It's heavier than the Higgs boson, it's heavier than all the other particles. And the top quark could have a very serious effect on the stability of empty space. So in the standard model, there are quantum effects due to the top quark, quantum effects due to the Higgs boson, and it seems that the effect of the top quark is to destabilize empty space. Now, this is not completely certain, and this is why it's important to study better the top quark. We need to know exactly what its mass is, and of course we want to look at other properties of the top quark. But the fact that it's heavier than all the other particles means that it plays a very important role in the standard model, and possibly, as I said, in the instability of empty space. At the moment we're doing experiments with the LHC, and we plan to continue working on the LHC for another 20 years. But already we're starting to think about what we would like to propose to build afterwards, what accelerator to build. And I say that there's basically two big ideas. One is to build a long, straight accelerator of electrons, so the electrons and positrons collide like this. And the other one is to build a circular tunnel like the LHC, but much bigger. And then the particles go around in circles and then they collide with each other. And those particles going around could be either protons or electrons and positrons. So CLIC is an idea for a long linear accelerator which should collide electrons at the highest possible energies. Alternatively, we have a project called FCC, so a future circular collider, so a big round tunnel for colliding protons and electrons. So at the moment we're studying these possibilities, and in about 2 or 3 years' time the CERN Council will consider these possibilities and give some directions for what it wants CERN to work on in the future. But at the moment we're trying to understand what physics you could do, what are the opportunities that these colliders would present. Serbia has been collaborating increasingly with CERN over the last 20 years or so. Perhaps it's worth remembering that Serbia, in the form of the former Yugoslavia, was actually one of the founder members of CERN back in 1954. So we were very glad 5 years ago to see Serbia come back as an associate member of CERN, and we're all hoping that next year Serbia will take the next and final step to become a full member of CERN. So in the meantime, there are Serbian physicists working on several CERN experiments, several different projects at CERN. So 2 of the big experiments at the Large Hadron Collider, ATLAS and CMS, they have teams from Serbia, and for example the Serbian CMS team played a key role in the discovery of the Higgs boson 5 years ago. There are other physicists from Serbia involved in other experiments, and what we all hope is that next year, when Serbia takes this final step, the way will be open for a deeper involvement of Serbia in physics at CERN. And with that idea in mind, it's recently been decided to set up an innovation center called Verrocchio here at the Institute of Physics, which will try to bring together scientists and engineers from Serbia, from CERN, from Italy and from Germany to work on the new technologies which are being developed to make the CERN experiments possible.